We can also look at things like, okay, what happens to these different parallel lines? Or these different straight lines. In a two-dimension image, like this square with a bunch of straight lines in it, we can see that some of the lines change in length, but they don't change in orientation. Other lines do change in orientation. They move, they change relative to each other, although they are still straight. So in any given homogeneous strain situation, if you went and had a whole bunch of these straight lines all through your object, in two directions they won't change. They will stay perpendicular to each other. This up and down line and the side to side line are perpendicular to each other on the left, and if we come over to the right, they're still perpendicular to each other. So they kept their orientation relative to each other. This is really important. These are the principal strain axes. These tell us where the most deformation has happened. Now, finite strain is the measure of all the strain from the beginning to the end. The whole thing. Incremental strain is the strain along just part of the path. Now this is good if we're going to take that heterogeneous total strain that happened and break it into a few homogeneous steps. Each of those steps is an incremental strain, part of the path from the original condition to what we have today. The strain path is the incremental steps in a specific order that it went through to get from its starting condition to its current condition. Sometimes the order matters tremendously. Sometimes, if it's a simpler case, the order isn't so important, but the steps are still vital. You can see here the top row and the bottom row started as circles and ended up as this ellipse on the right. But they took two different paths. The first one had 3 steps, and it ended up as this ellipse. The right one had 4 steps, and they started with a greater stress in the horizontal direction because it was squishing side to side and getting taller. Then the stress changed direction and squished it top to bottom, and it got wider. Whereas the one on the top, the stress was always in the vertical direction. It just increased how much it compressed over time. So if all we have is the final condition, it can be really difficult to know what the strain path was precisely and perfectly. If we have this ellipse on the right, even if we know, hey, this thing used to be a circle, we don't know which of these or some other possible strain path. We just know the final condition. Now, the next section talks about coaxial and non-coaxial strain accumulation. Strain accumulation is simply a bunch of strain happening and accumulating. It's that strain path, the steps along the way. And non-coaxial strain accumulation is when the principal strain axes rotate relative to the finite strain axis. So there is rotation. coaxial strain accumulation is when the principal axes do not rotate. Just a second. Sorry, there was an interruption. I had to pause that, so I know my train of thought's been broken. So I'll restart on the slide here, talking about non-coaxial strain and coaxial strain. So the non-coaxial strain accumulation is when there is rotation of the primary axes, so they're not in the same orientation as they used to be, and you have some shearing going on basically. Coaxial strain is when the principal axes do not rotate, they stay in the same orientation as they originally did, and so all of the strain that is accumulated is in the same orientation, or at least perpendicular. So you could be in two orientations, but they're perpendicular to each other, so it doesn't change. There's no rotation of the strain axes. Simple shear and pure shear. Two kinds of shear strain that happen, and if there is zero vorticity, no rotation of the strain axes, the strain history is coaxial, and we can have pure shear. Simple shear is when the distance to the shear plane remains constant. You think of a deck of playing cards and you kind of push on the side and it turns it into a parallelogram, but the thickness of that deck of cards is the same. It hasn't expanded or compressed. It's just changing the side to side stuff. So that is simple shear. In the real world, both of these can happen and at the same time, and this is called general shear. So if we look at a case of general shear, we can see two different types of actions going on. There's transtensional, which is shear with extension due to tensional stress, and transpressional, which is shear with compression. So in this first case, you can see there was tension in the up-down or Y direction, and they were shearing to the right in the X direction. In the second case here, there was compression in the Y direction and shearing in the X direction. This is called transpressional. So if we have all of these different things and we're starting to talk about them, we've got some pure shear going on. There's no rotation on the primary axes. Or we could have general shear, where the angles change. It's no longer perpendicular for the two primary shear axes, but the overall thickness hasn't changed. Simple shear, shown in part C here, where we have it's like the playing cards, and there is no other strain, so there is no other axes for the angles to change. It's just the shear. And then we have rigid body rotation, where there is just rotation within that object. We have some symbols or terminology that we use, and kinematic vorticity number, called WK, is calculated as the cosine of the angle. The angle alpha seen in B, so that general shear. And in a case of pure shear, this kinematic vorticity number, Wk, equals 0 because the angle is 90. Take the cosine of that and we get 0. Makes sense. In a case of general shear, it is some value between 0 and 1 because that angle is something between 0 and 90. In the case of the simple shear, the kinematic vorticity number equals exactly 1. Basically, that other stress axis has rotated all the way down so that it's part of that horizontal stress axis, and there's no angle. So the angle is 0, cosine of 0 be 1. Now, superimposed strain. This is getting into the real world stuff where you have a rock that gets deformed, and then that already deformed rock gets deformed, and then that already twice deformed rock gets deformed. It's superimposing the strain on the already existing strain. So a strain path is going to describe this superposition of a series of strain increments. Different events happen, the rock gets deformed multiple times. Trying to decompose this and see that strain path lets you figure out what it used to look like. So 2 or more separate events straining the same rock. That's superimposed strain. So a few different things can happen. Regions or parts of a rock can extend and then extend again, type 1. Compress and then compress again, type 2. Not really much different than if it had extended or compressed a whole bunch all at once, but it's still a case of superimposed strain. Compressing and then extending. Maybe it looks almost like it did originally. Maybe it looks very different. That's case 3. Case 4, extending and then compressing. Now, 3 regions for coaxial, followed by coaxial. So, region or type. Sorry, I was calling it types. They're regions. So, wow, my PowerPoint just went crazy. There we go. 1, 2, and 3 can be in coaxial, and then all 4 can be coaxial followed by non-coaxial. Okay, so the coaxial superposition, we've got types 1, 2, and 3 for different regions in the rock. We have 2 events. The first event had quite a bit of vertical extension and horizontal compression. The second event was also coaxial with a little vertical extension and a little horizontal compression. Now, these are 2 separate events. It's not taking the same object and same circle and saying, hey, I extended it and now I'm jumping over here. What it is if you had your original rock and you set, if you drew a circle on it before the event, after the event it would be elongated like the blue areas. If then you could jump in time and draw another circle right before event 2, after event 2 it would be distorted to look like those blue areas in event 2. The total is more elongation in the vertical direction than either of those two events, because it's the combination of those two events. So over here we have the total of event 1 and event 2. And there are regions of the rock, like up in the top here, that elongated, it extended twice. It extended the first time and it extended the second time. So now it's a lot longer. There are areas on the sides here, the light blue areas, that they shortened during the first event and they shortened during the second event. So there's a lot of shortening going on. That's a type 2 region. And then there are little regions here, these little wedges that are extra dark, that have type 3. Oh, the text is cut off a little bit here. This should say initial shortening followed by extension. So in the first one, they were part of this light blue area, like right there and right there, right there and right there. So during the first event, they were part of these shortening regions, or shortened regions. In the second event, they happened to fall within the dark blue and be part of the extension events. They were extended. So these little bits, these small regions of the rock had initial shortening followed by extension. In non-coaxial superposition, you have all 4 types. You have areas that, well, because here's your 2 events. First, it's a nice coaxial event with extension vertically and shortening horizontally. But event 2 had rotation as well as extension and shortening. That rotation is what makes it non-coaxial. And it was a non-coaxial superposition because that was superimposed on the coaxial initial event. So there are parts that extended that still extended again. So that's a type 1 region down here and up here. We have areas that shortened and still shortened again. So these are our type 2 areas, the light blue. We have some areas right here that were shortening and then followed by extension. So that's a type 3 area, right there and right there. On the other hand, we have some that were part of this dark blue extension that the second time, because of the rotated stress field, are part of the shortening zone. So those are type 4 regions, extension followed by shortening. So in the non-coaxial superposition, you have all 4 zones.